this result, we were talking about the Cramer-Rao lower bound. And so the main idea here is that this gives you a general lower bound on the risk of any unbiased estimators for quadratic loss, or just the variance of an unbiased estimator for quadratic loss. And the statement follows what we did in terms of this more, let's say, benign inequality, Hammersley, Chapman, Robbins, but requires some more regularity conditions. So we have the log likelihood, we have the score function, which is the derivative of the log likelihood with respect to theta. And the statement says if delta is an unbiased estimator for some g theta, and this g theta has a gradient with respect to theta, which we use this notation to represent. And then the main regulating assumption is this, the interchange of integration and derivative. Then we have this lower bound, which is if you think about it in the one-dimensional case, it's just the derivative of g squared divided by the Fisher information. This is a multivariate version where you replace the Fisher information with the Fisher information matrix. So the Fisher information matrix is basically the expectation of the score function transpose. So this score function is a vector, right? So if everything is in RD, this would be a d-dimensional vector. And this would be 1 by d. So d by 1, 1 by d. So this would be a d by d matrix. Rank 1, but we take the expectation. So the expectation is under the randomness in x. So these are all functions of x. And so this gives you the Fisher information matrix. And you can see that the variance of delta is lower bounded by this quantity, which is like a quadratic form, where this is the matrix of the quadratic form. So the inverse of the Fisher information matrix. So someone asked, what is the interpretation? Why, for example, we call this Fisher information? So the idea is the univariate case, if you look at the result, it's just saying that the variance of variance of delta is bigger than or equal to this quantity. And for example, theta is the identity map, right? So so let's say we're just estimating, so we do it somewhere else. So omega is a subset of R, so D is equal to 1, and then we're doing g theta equal theta. So g dot of theta is 1, so this is just saying the variance of delta is bigger than or equal to 1 over I theta. Okay, so this is perhaps the simplest form of the Cramer-Rao lower bound, and it tells you that if I theta is large, then this lower bound is smaller, so the variance could be smaller. So that means the model has more information about the parameter at this particular value of the parameter. It's also a bound that depends on theta, which information is a function of theta. So at different locations, at different parameters, you have different amount of information. Sometimes the I theta might be fixed. But in any case, because the variance, the lower bound on the variance is the inverse of this, so this acts as some form of information, right? So the inverse of the variance is some sort of a precision. So how much accurate you can get, and this controls how accurate you can get, assuming that this lower bound is tight, which may not be always. Okay, sounds good. The meaning is clear, right? And then what we did is we tried to prove this result, and the way we prove this, we rewrite this as a differential inequality or equality, and this differential equality holds for any to C. sort of. And so if you apply it with c equal 1 and delta, in the univariate case, you would get that the expectation of the score function is 0, and that the gradient of g theta, so that would be the mean of the delta. Let's say if I apply the delta, the gradient of g theta is equal to this covariance. So when you plug it into the information inequality, you get the bound, because this is going to be the variance of L dot theta. So you're applying it the covariance inequality to delta and this guy, the score function. And so the covariance would be this guy squared, and the variance of L dot theta would be the Fisher information by assumption or by definition. So in the general case, as I mentioned, what you would do is, instead of applying it to the score function, so you're going to apply. So we had this Cauchy-Schwarz inequality, right? So this was the variance of delta bigger than or equal to covariance of delta and psi divided by the variance of psi. So in the univariate case, I can take psi to be the score function. In general, for the multivariate case, you take psi to be the A transpose times the score function. Okay, so A transpose is, so A is just a vector. So A transpose is a deterministic vector. This is L dot theta, so the result is a scalar, so 1 by 1. Now I can apply everything to this. A little bit of calculation shows that this is still 0 mean. And because the expectation of this is just A transpose times the expectation of the score function, which is 0. So this is 0 mean. And then you would do the calculation, just apply let's say if I want to calculate the covariance of delta and this guy, because it's 0 mean, it would be equal to this, right? Because A transpose. So I'm calculating this part. So if I do that, this is equal to that because this quantity is 0 mean. And then this quantity is equal to this. Why is that true? I can pull A transpose out. Why can I do that? Expectation is linear, so if you think a little bit about this, A transpose comes out, so this would be really equal to A transpose expectation of delta L dot theta. Now delta is a scalar, this is a vector, so this whole thing is a vector. And this guy we calculated by this calculation that we had here, this is just gradient of expectation of delta, right? So gradient of so I'm applying it with delta here. So this would be the gradient of the expectation of delta, which is g theta. So this would be really gradient of expectation of delta, which is really what we call g dot theta. So this turns out to be that. And then for the variance, you also have to calculate the variance. So that's the calculation of the variance. So variance is equal to this. So why is that true? There is a bit of trick going on here as well. Yeah, so this is 0 mean, so variance of A transpose L dot theta is really the second moment. A transpose L theta dot squared. So then what is the next step? The trick is to write it as A transpose L dot theta times itself. Right. And a little bit of trick. Another piece of trick is I can rewrite this as L dot theta transpose times A. Why is that? Just yeah, it's a scalar transpose of it itself. So if you transpose it, you get that. Then I can ignore the parentheses because product has like, you can just ignore the parentheses. There's a property of product that says that, right? What is that property? I forgot, associative property. So it doesn't matter where you put the parentheses. I can just, for example, put the parentheses here. Okay, and then I can pull A's out. Again, this you can argue for yourself because of the linearity expectation, the A comes out from both sides. This is linearity of expectation. So if you have trouble with this, just write this in terms of the coordinates. Okay, and then expectation moves past the sums. And then you can put it back together. And this by definition is the Fisher information. Okay. So what we get is that this is the variance is the Fisher information. So once you plug everything in, so we have calculated this guy, this turns out to be that. So you get this squared. And the other piece is variance. So this is the variance. So I have this lower bound. And as we discussed earlier, this holds for any A. Now I can optimize over A. So that will be a purely optimization problem. So I want to maximize this bound to get the tightest lower bound to maximize this over A. For simplicity, you can call these some, because these are fixed. So this is some V, this is some B. And if you think about it, you're basically solving this optimization problem. A cannot be zero, obviously, because the variance would be zero, we're dividing by zero, but otherwise A can be any vector. So this is optimizing A in RD, not including zero. And I believe this is either an exercise that you're going to turn in, or you can do it as an exercise. This is just an optimization problem. You can solve it. And the solution is V transpose B inverse V. Okay. Just a ratio of two quadratics. So the maximum would be this, and you can read it that it's just G dot transpose Fisher information inverse G dot. Okay, so it's not nothing tricky except these two ideas of applying the Cauchy-Schwarz. The Cauchy-Schwarz is the basis of these bounds. The trick is to use this psi carefully. So either score function in the univariate case or a linear combination of the elements of the score function, or linear projection if you want. And you do this and then you optimize over these weights. And so this gives you the general form. Okay, sounds good. Questions? There are a bunch of tricks here. So how to calculate the variance, I encourage you to go through it for yourself if it was quick. If you haven't seen it, this is basically saying, so this calculation that we did, if I do it, for example, in another course, I would say something like covariance of A transpose, let's say Y, if you have a vector would be, or the variance would be A transpose covariance of Y, A. So this is the covariance matrix of A. The variance of a linear combination of a vector can be written like that. So this is the general idea. Here we are using that, basically the covariance of this guy, this random vector is just the Fisher information. So general result, it's always good to remember this. For a random vector. Okay, questions? Okay, a couple of comments. Regularity conditions are key. So if they don't hold, the result is not necessarily true. Unbiasedness is also key. If the estimator is not unbiased, then the variance could be smaller. Anyone can give me a counter, like an immediate counter example. What an estimator who's like unbiased and violates the Cramer-Rao lower bound. And then not unbiased, biased. A biased estimator that violates this. in general. If I don't care about the bias, how can I drive the variance to 0? Just the constant. Yes, just the constant estimator would violate this. It's severely biased, but variance is 0. So if you care about the variance only, you're in good hands. There are a lot of those. But yeah. So this is easy. So under the same assumptions of regularity, then you can show that there is another expression. So you can take the Hessian or double dot of the log likelihood ratio. That would give you a matrix. The negative Hessian, if you take the expectation, that would also give you the Fisher information. So you'd see these two expressions. Sometimes this is easier. Sometimes the other one is easier. So the other one is more statistically more probably relevant because that's the covariance of the score function, variance matrix. But this one is also equivalent or like equal under these regularity assumptions. So you take the Hessian, which is a D by D matrix, and then negative of it, and then take the expectation. Double dot means the Hessian. So this guy measures the Fisher information. Another interpretation is that measures the expected local curvature of the likelihood you can see here, or the log likelihood. So this interpretation or this expression, this is the curvature. The Hessian measures how curved things are. So a linear map, for a linear map, the Hessian is 0. There's no curvature. But for a quadratic, for example, you would have like positive curvature. This is negative curvature. Or it might be like saying positive and negative differently. But what is it saying? Because Fisher information we'll see, or we don't have to see. We define it to be the covariance matrix of something is positive semi-definite. Okay. So in the univariate case, it's going to be really positive or non-negative. Really, information hopefully is not negative. It's either 0 or so. Fisher information is positive semi-definite. So the situation would be like this, because the negative, so the Hessian would be negative definite, or like in the univariate case, think of the univariate case, the second derivative would be negative, so that the Fisher information is positive. So you have like a curvature, like curved like this at theta, and the more you have the Fisher information, the more curved it is. And so the more curved it is, it's easier to estimate theta because you sort of can recover the likelihood from data, and then you want to map the likelihood to the parameter. Okay, so the more so you can figure out where the maximum is, sort of the likelihood. So this is the expected likelihood. And once you figure it out, if the likelihood is very flat here, so if you have a very flat likelihood, even though you find like roughly the maximum, if you perturb it a little bit, there's a wide range of values that theta could take. But if the likelihood is very curved, if you perturb the likelihood a little bit, the range of the values that theta can take is very small. Okay, so that gives you the intuition that the more curved this is, because I can like estimate the maximum sort of by, so hopefully the maximum, the location of the maximum hopefully is, we'll see, like the expectation, the expected. So you'd hope that the expectation of the negative L theta sort of, this has a maximum at, or sorry, not the negative, the expectation of this guy itself. Under the true parameter, we'll see this is related to the KL divergence. So if I take the expectation under the true parameter of L theta, I would hope that it achieves the maximum near theta star. We'll see. And from data, I can get an approximation of this from IID data. So this is general, but in the IID case, it's much easier to see. So yeah, if I want to maybe. So okay, so let's work through that. It might be worth it. Should have probably. so let's I'll come back to this, but the point is let me make the point that this is general, okay, but in a case where let's say x1 up to xn are like IID from let's say a p, how should I write it, like p1 of theta if you want, or okay, I'm gonna write p theta. Okay, there's this density, univariate density. If you want to think about the Fisher information for this entire family, this joint distribution would be, you know, it's like the density would be the product, right? So what we really think about is this guy, which I'm going to call this P. Okay, let's do 1. Okay, this is really now P theta of x. And so the model is this, and the Fisher information would be, the log likelihood would be log P theta of this x. So that would be my, so consider the IID setting. So this is not general, but it's easier to talk about. Consider the general, the like special case of IID sampling. So this would be L theta of x. X here is this entire thing. Okay, if you want, I'm going to write like this here so that it's a little bit more clear that this is a vector. So this would be summation I from 1 to n log p theta 1 of xi. Okay, and then if you imagine see if I have it here. No, I didn't mention the so let's say 1 over n L theta of x. What does this converge to as n goes to infinity? So this is something that we come like discuss hopefully in a few lectures. But this is easiest to see like what Fisher information is doing asymptotically. So we haven't talked about asymptotics, but this is the setting up asymptotics. If I let n go to infinity, this is basically going to be it's like an average, right? Normalized log likelihood. So anyone knows what this is going to converge to? It's an average of if you want, I can write something like 1 over n. These univariate likelihoods or like single. I'm putting 1 to denote that this likelihood is for one sample. So this 1 over n times the likelihood of the likelihood of the model based on the entire sample is like the average of the likelihoods for a single sample like evaluated. So this is a sum of like average of IID entries. So xi are IID. So we're assuming that, let's say I'm going to assume that these are coming from p theta star, there's a true parameter that generates the data. So under that true parameter, what would happen here? Anyone remembers, like there are two results in probability theory. One tells you what this converges to. Entropy. Like a little bit basic. Just the average of a bunch. So okay, so we have Z1 up to Zn, their IID from some distribution. So what does this converge to? Expectation of like a single one of them, if they're IID. What is this called? Law of large numbers. Okay, great. So this is one of the like the two famous or like the two key results in theory. So if that's the case, that's similar. So these are like ZIs, right? So these are IID random variables. They are from the same they have the same distribution, because xi's have the same distribution. This likelihood is like a nonlinear function applied to them. So what does this converge to? Converges to the expectation under star of the likelihood of one of them. I'm going to write x1, the generic. Okay, so now you see what I meant here, that it should be like this. So this is like the population version. And so if you do maximum likelihood, for example, you're going to try to maximize this as a function of theta. Asymptotically, as like you get more and more samples, you're hoping that you're going to converge to this. And so this guy is like non-random. And this will have some sort of a, usually, I mean, hopefully, this is going to have a maximum at theta star. So the only, if you plot this as a function of theta, so this is theta here, this is this guy. Let's call this, I don't know, f theta. At theta star, it's maximized and then goes down. This we'll see. This is going to be the Kale divergence between p theta and p theta star. But that's if you believe me, that's the case. But what I get is like this noisy version. So I'm going to observe this. So this would be something like this, right? So when you try to maximize, as asymptotic as n goes to infinity, this is going to converge to that red line. But what happens is that I'm gonna make an error. So instead of like the actual maximum, this point might be the maximum, right? This might be the maximum. So that will be the maximum likelihood. And the difference, you can see the difference is going to be related to the curvature of this guy, sort of. So if I make, if these deviations are the same, but if I sort of have a very flat likelihood, it could be that I make the same sort of error, the same amount of error, but it might be like I like the maximum turns out to be this, for example, like not very good. Right? So there are fluctuations, right? By chance, I could be like the maximum could be here. That's the theta hat. And this is really theta star. So if there's a flat, so I'm going to be guaranteed that like asymptotically as I get these fluctuations going to converge to this. But there is fluctuations. And when I try to estimate my parameter, I'm going to by chance like be off. If this is very curved, if I'm off, I can't be too far from this. But in this case, the flat case, I'm going to be very far off. So when you want to translate deviations. So deviations in the x-axis, if I translate them to the deviations in the y-axis, deviations in the y-axis. So I'm going to be guaranteed that my maximum is going to be within this range of the true maximum. Then the entire band here is the possibility for theta. So you can see like the interval that I get for possible maximum likelihoods is large around theta star. And for example, if I get the same sort of kind of band here, I'm guaranteed that I'm going to maximize within this tolerance, then my range is going to be like smaller. So this nicely captures the amount of information. Okay, so and if you take the double derivative inside this, that will give you the Fisher information. Okay, so under so it would be the Fisher information evaluated at this point. So take the double derivative inside negative, and then evaluate the theta star. So theta star, theta star, that will be the information will be the curvature at that point. So this is a little bit subtle, but the curvature of likelihood tells you like how much information you have. This is a little bit beyond. So this analysis, like short analysis that we did, is beyond the Cramer-Rao bound, and sort of this this lies at the heart of trying to make Fisher information asymptotically more like it's a little bit more fundamental. So when you try to expand the likelihood, the second derivative of the log likelihood is sort of controlled by this. And asymptotically, that second derivative that controls the curvature. Okay, so this was some sort of a little aside of what this means. Okay, any questions? So we get to talk about this kind of ideas later more. but this is just a good place to discuss them as well. Questions? So you now understand what the Fisher information means at a different level. Yes.
When estimation, what really matters is the Euclidean distance between theta star and theta hat, or the like a KL divergence between the distribution represented by theta star and theta hat.
So that's up to you. In what measure you want to measure the difference of these, that's up to you. That's your loss function.
So if we use KL divergence or Western distance, I would say if the log likelihood is more flat.
So this turns out, okay, so this turns out to be negative. We'll see what KL divergence is, but KL divergence between these two densities, the true density and the density p theta that you evaluate. So this is really a measure of loss between the two densities. And at this level, it's fine. So if you want to measure your distance of the parameters in terms of the distance of the distributions, you're not going to pay this price. But usually you care about the parameter. Once you want to translate that into the parameter, then this distance comes in. If you don't care about the parameter, then we're fine. Okay. We're going to see this a little more later. When we talk about consistency of the MLE. So any questions? Is this sort of rough picture? This has a lot of intuition behind it, but we can come back to it later. One point to also note is that you're going to run into this issue in your homework problems. You have the Fisher, if you have IID setting, there is a Fisher information associated with the entire sample, and there is Fisher information associated with one sample. And if you imagine what this Fisher information is, which is the, so if you think about this interpretation, expectation of the negative second derivative, when I take the, think about this, when I take the second derivative of this, put a minus sign and take the expectation, it would be the summation of I from 1 to n of negative the second derivative of these expectation. So what happens is the Fisher information for this model is really easy to show. Would be summation I from 1 to n of the Fisher information for each one of them, and each one is like exactly equal, so it would be like n times something like that. So the Fisher information based on one sample times n would be the Fisher information for the entire thing. So Fisher information is additive. In general, if you have IID, not IID, but independent samples, the Fisher information that they bring would add up. Because here we have IID, the Fisher information, each one of the samples is exactly the same. And so when you add them up, it's just n times. So it like linearly increases. And just very nicely sort of matches the idea that information is accumulating by IID sampling. And this is easy to show. If you understand this notation that I used here, this is based on one sample. This is based on the entire sample. The difference is just that the log of the summation is summation of the log, and then you take the derivative. So that's this comment. Fisher information is additive over independent sampling. There's one comment here. Attainment of Cramer-Rao bound is related to the attainment of Cauchy-Schwarz. Someone in a previous class found a paper that talks about this if you're interested. And it turns out that, I mean, if you believe that paper, they show that this happens if and only if you're in an exponential family. So I don't remember exactly, but if you want to read the paper, attainment means is there an estimator that attain this bound? So is this like tight? This is sort of true. I think there are some caveats. So Fisher information is not invariant to reparameterization. That's one of the issues that probably again you'd see in your homework problems. If I reparameterize, for example, you saw that we have at least two relevant parameters in exponential families. One is the canonical parameter, the other is the mean parameter. So if you reparameterize in terms of mean, take the Fisher information with respect to mean, it's not going to be the same as the Fisher information with respect to mean. You see there the derivatives involved, and there's like a chain rule, so there's this thing coming out. Like the derivative of the parameterization with respect to the other one. like in general, the determinant of Jacobian or something like that. That's fine, but the Cramer-Rao bound is a statistical property, so this cannot change. By your parameterization, you cannot improve the information in the model, and it turns out that this is invariant to reparameterization. So when you reparameterize, you change both this G and this I, and the changes would cancel each other out. So the Cramer-Rao bound remains the same. This all follows from the chain rule and sort of things canceling out. And it's a little bit of like fun little calculus exercise to try to show that. But again, statistically, it all makes sense because the Fisher parameter tells you about how accurate you can estimate that particular parameter. So if you change your parameter, you change the geometry of the likelihood. One parameter could be easy to estimate, the other one might not be. But if you have like a function of your parameter which is invariant, so let's say g theta is computed in terms of both like mu or theta, that thing is not changed, then the Cramer-Rao bound cannot change for that as well. Okay, these are the comments. Some more important than the others, but any questions? So this Fisher information is going to pop up everywhere in a statistics, so like traditional statistics. So it's a very important quantity. So an estimator, for example, that achieves this sometimes is called efficient. So if you have an estimator that achieves this Cramer-Rao lower bound, they say that it's an efficient estimator. So its variance is small as possible, at least among the unbiased ones. Questions? Cramer-Rao bound is good enough. Like, are we happy with statement, meaning, sequences? Okay. One more thing and just move on. This is not that I'm not going to spend too much time because we already spent too much time. So you can extend this to multivariate parameters. So G used to be from RD to R to R. Now think of it as RD to RM. We can have a rule that's unbiased for G that makes sense because the expectation sort of doesn't care much, but the variance is a little bit tricky to define, but we can think about covariance matrices. So if delta is an estimator and an unbiased estimator of theta, what this is saying is that delta is from R, like not from R, from whatever X space is to R M, right? And so both of them are in RM. So this is in RM, and this is also in RM. But there is no single variance. We have variances of the components, but there's a covariance matrix. So this guy has a covariance matrix. And we can think of this as what we try to lower bound, and there's an analog of the Cramer-Rao bound would be something like this. The covariance of this is bigger than or equal to, this replaces G dot. So this is now the Jacobian of the transform, which is a matrix, partial derivatives of Gi with respect to theta J. Fisher information remains the same. So this would be like M by D, this would be D by D, this would be D by M. The only thing that remains, this is proven exactly like the way that we did for the Cramer-Rao bound, but we also like apply a U transpose to delta to make it scalar. So U transpose delta and then A transpose times the score function. Both are scalar. Now you work with these two, and you don't need to do the A transpose score function because we already did that. So this is now a univariate estimator of U transpose G theta. This is going to be unbiased for U transpose G theta. If you write down what exactly we had for the Cramer-Rao for this estimator, then you can optimize over U. And this result follows. The only question is what this means. What does it mean for a covariant like a matrix to be bigger than the other one? And this is in this positive semi-definite order. So the meaning of it is exactly that. So A is bigger than or equal to B if A minus B is positive semi-definite. So what this is saying is that the covariance of this minus this other side is positive semi-definite. So you translate this gives you a lot of information. This, for example, tells you the variances of these guys are bigger than or equal to U transpose J theta I inverse J theta transpose U. And this is exactly the statement that you're going to prove that for all U in RD. And in particular, if I take the U to be coordinate vectors, tells me that the variance of each coordinate is lower bounded like that. So you get lower bounds on the variance of each coordinate, but you also get lower bounds on the variance of all the kind of linear combinations of the coordinates. Okay, it's just a little extension. As an exercise, you can try to go and prove it and interpret it. There's a link to the Gauss-Markov theorem. Anyone knows what Gauss-Markov theorem is? So OLS has the smallest variance among unbiased estimators in linear regression in the Gaussian setting. So if you imagine like you have y is normal between x beta or x theta sigma squared I, that's the linear regression model. You try to estimate x, ordinary least squares is an estimator. And if you use this result, you can show that the covariance of the OLS would achieve this lower bound. So it's the best unbiased linear estimator and the Gaussian like, linear model. Just check this out. And this is something that you could do as an exercise. Okay, so it's like a special case of this when you have that. This is a side note. This is usually talked about in a regression course, but it's just a special case of that. Any questions? This was a little bit fast, but this is like a side note overall. The entire it's like a slide. Once you understand like this sometimes called Cramer device, then this is easy to, this is the Cramer device. So how to translate, like how to deal with a vector by linear projection, then this is just an extension of that idea. Questions? Yes.
I have a quick question. So with your vector, you could choose it to be like where like the ith element is just a 1 and the rest are zeros.
Yes.
And then you just get that particular
Right.
ith element is like you get the lower bound.
Yes, exactly. That's what I like mentioned. So if you take the basis vectors like 1, 0, 0, 0, this would give you delta 1. So that's saying that the variance of that first coordinate is lower bounded by this like exactly what this is.
Okay.
And so you get lower bounds for the variance of each coordinate. Good. And but you also get more. So you can, for example, tells you something about the covariance structure as well. Like if I want to like, what is the variance of delta 1 plus delta 2? Smallest that it can be gives you lower bound. Questions? Okay. So here's a simple example. We have xi's. We have like the more general version here, but the very simple case is like xi's are theta sigma squared, normal location family, sigma squared is fixed, g theta is theta. You write down the likelihood. We have this expansion as we saw, everything is ID, you get a summation of want to be careful, this should be 1. So this is the p theta based on 1. This is the better notation. And so what you get is that expression you can calculate, and then you take derivative. The first derivative gets rid of the constant, you get this expression. At this point, you can easily verify if you take the expectation of this. The expectation is 0. So the score function is 0 mean. That's always a good check. if your regularity conditions hold, this has to have zero mean. If it has zero mean, take expectation. Expectation of this would be each one is zero mean, and so that, and then the second derivative, we get rid of the extra. So you can see the second derivative is just constant, basically. The negative one, you get negative n over sigma squared. And so when you take the expectation of the negative of this guy, you just get back n over sigma squared. And the Cramer-Rao bound in this case says that the lower bound is sigma squared over n, which is the inverse of the Fisher information, right? So that's I theta. And this is not surprising. In this case, it's achieved by the sample mean, and so the Cramer-Rao bound is tight. Okay. You also know that the sample mean is U of U, so you could have derived this. So this is an exponential family, one-dimensional, full rank. You know that the sufficient statistic, once you write it, the sufficient statistic would be the summation of xi's, or 1 over n summation of xi's if you want. And so that's unbiased for theta, and it's based like a function of the complete sufficient statistics as U of U. So you know that the variance of x bar is actually the lower one. So that's what you have. And this gives you an easy way of providing a load. Okay. Here's a more general example, like that was a special case of this. So xi's are, let's say p theta 1 if you want, of xi. And these are from the exponential family in canonical form with sufficient statistic t. So when I assume that these are IID, when I write down the joint distribution, again, it's going to be a summation, right? So log t theta of x1 up to xn would be like summation I from 1 to n log p1 of xi. And then by the exponential family nature, this turns out to be exactly this. So the x goes away, summation comes in. There's a constant which is related to h. We don't care about the constant because the score function, when you take the derivative, this goes away. So the score function would be so L dot theta is the derivative of this. So when I take the derivative of this, what do I get? Derivative of the first term, summation I from 1 to n tx I. So that's this part. This is a linear term. And the second term is negative n times the gradient of a theta. Okay. At this point, we can verify that indeed a score function is zero mean. Is it really zero mean? Sorry, this should be L theta of x, let's say. Is it zero mean?
Gradient of is.
Yeah, gradient of, right. So this is basically the expectation of one of these. These are IID. When you take the expectation, you get n times basically that mean parameter, which is the gradient. So this actually turns out to be zero mean. Just remember that this was the mean parameter, right? The expectation of t of, let's say, xi in this case. So how about the second derivative? When I take the second derivative, the first term is constant, goes away. The second term would give me negative n times the Hessian of a. So, and then I put a negative sign, I get n times the Hessian of a. Okay, and we also recognize that the Hessian of a is covariance of t. Let's say t of xi if you want, t of one of them. This is covariance of t evaluated at one of these, like in the univariate model or single sample model. So this was another one of the differential inequalities. Okay, so why this is interesting, because sort of tells you that the Cramer-Rao bound is attained, and to see it, it's easiest to see like 1D case, n is equal to 1. So this is a d-dimensional family. Let's say d is 1. We just have one sample to avoid confusion. Then let's say I want an unbiased estimator of this mean parameter. That's my g of theta. Okay, to see the significance of this result. That's expectation of t. It's like t of x1 or x, because there's just one of them, and this is the derivative of a. Gradient reduces to a derivative because t is 1. And so this is the Cramer-Rao lower bound. Mu prime theta squared divided by I theta. Mu prime would be the second derivative of a. So that's this because of this relation, right? And then the Fisher information from this expression, we have that it's like the second derivative of a as well. So one of these cancel out, I get the second derivative of this, which is the variance of t. Okay, so it's saying that Cramer-Rao lower bound is equal to the variance of t. So this is a lower bound on the variance of any unbiased estimator. So unbiased for mu theta. And what it's saying is that because t is also unbiased for mu theta, it's saying that Cramer-Rao lower bound is actually the variance of t. So t is the un here. T attains that smallest variance. So we've proven that t is the un vu in this case without completeness. Sort of. So attained by t. There's a little bit of general case of what happens. You can read this for yourself, but it's just in the exponential family, if it's full rank, it doesn't give you extra information. Okay, you already hopefully know that. This is so t is UMVU for the mean parameter for its mean, but this gives you an alternative way of proving. And you can see the attainments as well. So Cramer-Rao bound is attained. Okay, sounds good. Okay, one last example. I'm not going to go over the details of this. If you're interested, you can figure out the details, but this is an example where attainment fails. Okay, so this is an exponential family. Okay, and you have a Poisson between lambda, like parameter lambda. You have an IID sample. Sufficient statistics is x. Mean parameter is lambda because the expectation of x, you know that it's lambda. So the mean parameter is actually the parameter that we are familiar with. This is expectation of t. So the sample mean, we know that it is Cramer-Rao bound for lambda. We just showed that, or we can also argue the completeness. However, let's say I want to estimate like lambda squared for some reason. Okay. You can calculate the Fisher information, and then you can calculate the Cramer-Rao bound. I'll leave the details to you. So Fisher information turns out to be that. You should be able to do it like, sort of without much work actually. And the Cramer-Rao bound turns out to be this. On the other hand, it's not hard in this case to come up with an unbiased estimator for lambda squared of this form. So if you're familiar with Poisson, this is unbiased for lambda squared. So the expectation of this is lambda squared. And so this is going to be unbiased, and you can calculate the variance of it, and it turns out the variance is quickly bigger than Cramer-Rao bound. And because the summation here is complete, so we know that this is complete sufficient. If we Rao Blackwise, so this estimator is unbiased. If I project it onto the sufficient statistic once, I know that I still get an unbiased estimator, and it's going to be a function of the complete sufficient statistic. It has to be UMV. So if you do that, again, a little bit of exercise here. It turns out to be S times S minus 1 divided by N squared. And this is going to be UMVU. And you can calculate the variance. And the variance turns out to be still bigger than CRV. Okay. So so this entire thing as an exercise would be an example where Cramer-Rao bound fails. Not fails, but it's not the thing. So there's a UM view is very strictly bigger than what Cramer-Rao bound suggests. Okay. There's a little bit of work to deal with this, but there's some nice ideas of trying to come up with an unbiased estimator and then projecting green all likewise to get the UM view. And the UM view turns out to be the SCRV. Usually there are a bunch of typos in this over the years. It has been fixed, hopefully. But if you found any typos, let me know. Some of the calculations are a little bit tricky. But because this doesn't give you much information, I'm not going to go over the details. Questions? So Cramer-Rao bound is not always achieved. But still gives you a reasonable bound. So you can see there's like a term here, which is this, and there's an extra term, which is not sort of quite this one, like a lower order. If n squared is correct, this is the main piece. This is of the lower order. So up to the first like term, you capture the bound, but there's a bit of correction there. Questions? Cramer-Rao bound Fisher information. Okay, so let's leave this aside. Yeah, nothing there. Finally, let's get back to like decision theory and a bit of like useful stuff about Bayesian method. So we took a detour into like so we started with decision theory, took a detour towards like from like the sufficiency, minimal sufficiency, went back to decision theory to talk about UMVUs. So sufficiency, minimal sufficiency, completeness. And then we talked about UMVUs. That's one way to deal with the fact that risks are not comparable. And then we talked about exponential families that gave us a lot of information, like not a lot of information, but a lot of interesting families of probably distributions. We talked about Cramer-Rao bound, which gives you a lower bound on the variance of unbiased estimators. Now we move back to, if you go back to the very first slide or the very first lecture, another way to deal with the risks not being comparable directly is to summarize them by a number. Okay, so you could take the average of the risk, or you could take the maximum, or you could do something else. If you take the average, that's very close to the Bayesian approach to statistics. So I'm going to like talk a little bit about that, which is very useful, sort of like a big camp of statisticians or Bayesians. It's useful to understand that. The perspective that we're going to follow here is like frequentist view of Bayesian approaches or decision theoretic view of Bayesian approaches. Not necessarily what Bayesians view their approach or how they view it, but mathematically it would be equivalent, or like this gives us some like information about the decision problem. Then we're gonna hopefully talk about the minimax as well. Okay, what happens if I want to minimize the maximum risk as opposed to an average risk? Okay, so let's start with the Bayesian approach. So how many people know Bayesian statistics or Bayesian approach? So anyone wants to like enlighten us about the Bayesian approach? So what do Bayesians sort of like? How do they do statistics? Yes.
You assume some prior information about the distribution and then update the prior as you call it data.
The prior information about the distribution. Okay, so that last word you have to like clarify what distribution. So you have prior information about something, right? So we have observations, right? And we have something else, right? So observations always have a distribution in statistics. So that's shared by frequentists and Bayesian. So you assume that the distribution, there is a distribution that you draw your observations from. But what is the difference between like frequentist and Bayesians after this point? Yeah.
Yeah, so remember the like plot we had at first. So we have a risk function as a y-axis and the values of the like the parameters as the x-axis. And so for the Bayesian method, I think like we assume there's a prior based on theta. So there's a density function for theta. And what the Bayesian statistics is like, it's like we are calculating the average, like, or maybe the area under the curve.
Under the risk. Yes. Okay. Great. So the way that I introduced the Bayesian approach is from a decision perspective, you had this risk as a function of theta, and then you can put a distribution on theta here, like a weight on theta, and then average out the curve over theta. It would be like the integral of theta with respect to the weight on the theta axis. For example, theta is uniform 0 to 1, you just take the area. And that summarizes this curve nicely. For another estimator, you would get that. But if we like step back before talking about risks, we can do Bayesian analysis as well. So the Bayesian analysis is basically, so if you want to put it in the framework of decision theory that we talked about, like a little bit of decision theory is not bad before we get to the risk. So we have these parametric families of distributions. Oftentimes we assume that they have densities, right? I'm going to write it like that, with respect to some density with respect to, not this. This was like a bit density with respect to some measure, like the Lebesgue measure. So we had these densities and we work with these densities. And so you have a parametric family of densities, right? For example, these could be like e to the negative x minus theta squared over 2, or like product I from 1 to n. Yeah, 1 over root 2 pi or something like that. So there's like parametric family of distributions for your observation. So what is that like frequentists do is that they view this parameter as just a fixed parameter, like not fixed, but deterministic parameter. So it parameterizes the distribution, but there is a true one. Like there is an actual one. We don't know which one, and we don't want to assume anything about it. It's just that we know that there is one true one, but anyone could, like any one of them could do. And so they view this as a family of distributions. What Bayesians view this, you can think of this p theta of x in the Bayesian framework as this is being the density of x given theta is equal to theta. So theta is really a random quantity. What this is telling you is the density of x given theta. So what a statistician would say is that this guy, like x given theta, I'm writing capital theta to denote the random variable theta. If it's equal to a theta, then this is coming from p theta. Okay, it's a condition on theta being equal to a particular value. The distribution of x's follows that. For example, normal between theta and variance 1. But then they also assume that this has a distribution. So that's called the prior. So you can assume that this theta itself is random. For example, this could be, if we can assume that this is a gamma distribution, for example. I know, for example, that theta is positive, for example. Okay, I put a distribution on it, whatever I want, and so that's called the prior. So this summarizes your prior knowledge, prior on theta. Okay, so Bayesians assume the parameter to be random and they put a distribution on it. Okay, and this leads to the idea that if you view the decision theory framework, as we'll see, it's as if you're averaging out the risk. But if you don't care about the risk, so this is a valid framework. So what they do then is, what do they do? So we have this. What is the next step in the Bayesian approach? How do they estimate the parameter? They form the posterior. So what is the posterior?
Yes, theorem
Sorry?
should be
so this is the likelihood, right? So you can explain what it is. What is the posterior?
There's the distribution of theta given some observation.
So the distribution of theta given x equal, let's say, a particular x that you observe, this is called the posterior. Okay. So I assume that x given theta has a certain distribution. That's my likelihood, basically. If you want to talk about, like, be a little bit not precise, it's like equivalent to likelihood once I fix x. Once I fix x, you'll see why they call it likelihood, because when you write down the posterior, you really that component, that this distribution contributes the likelihood to the posterior. And then there's a prior distribution, and then I invert or reverse this or invert this relation. X given theta, I translate it into theta given x using the Bayes rule. That's what is called the Bayesian approach. And that's the end of the story. The entire Bayesian sort of analysis is this. So come up with this. Usually this part is agreed upon by statisticians, at least, like frequentists or Bayesians. This part is controversial. Bayesians sort of come up with this somehow. But once you have this, there is a nice posterior here. Posterior of theta given x. So this x is the one that you observe. So condition on the x is the x that you observe. Now you have a full distribution on theta. This distribution is very different than the prior, usually much more concentrated on a certain part. And that tells you all you need to know about your parameter. Okay. It also has that uncertainty built into it. So because this distribution has a variance, so you can not only get like the center of the distribution as your point estimate, but you can also get like a nice distribution around it, how like variable it is. Okay. So the entire like Bayesian framework is summarized in these like 3 steps. Okay. Likelihood, put a prior, and then posterior. I'm going to write some like formula as well. But that's the story. So what does it have to do? Any questions? So far is like clear or like familiar to people. We'll see more details. But what is the relation of this to decision theory? Or what is like, can I like justify this posterior in terms of decision theory? And the answer is yes. So if you want to like take a detour into the decision theory land, so we can put this on a decision theory framework. So we interpret these probabilities as the conditional densities of x given theta. So formally what this is saying is that t theta of A is really probability that x belongs to A given theta equal to theta. That's the formal way of writing it. We put a marginal distribution or prior on theta. So once I have x given theta, and I have the marginal distribution of theta, this gives me the joint distribution of x and theta. Okay, I have a full specification of this joint distribution. Okay, if you remember x given theta and theta gives me the joint. And then I can talk about, for example, this guy. Okay, so let's work out with the frequentist version. So this was the frequentist risk of an estimator, if you remember. So I have a loss. I evaluate the loss as theta and the 0, take the expectation, that would be the risk. Now I treat this as this expectation of theta, I'm going to write it as expectation conditional on theta. Okay, that's like a Bayesian view that this is really taking the expectation of this whole loss, but conditional theta. That's just based on, remember, this is based on the distribution of x being p theta, but that's exactly the conditional distribution of x given theta. So if you view it that way, then you can like erase this theta, like it's just imagine this holds for any theta, so it holds for a random theta, so I can really write something like that. Okay, just plug in capital theta everywhere. So this is saying this is a random quantity, conditional expectation of this given theta, this is going to be a function of theta, this turns out to be the raised value of theta. And now I take another expectation. By smoothing, this would be just the full expectation of this guy. The full expectation of this guy or the expectation of this risk. This is called the Bayes risk. So if you think of this, the average, this would be really the average. R theta delta, we can say pi, I forgot what I called it lambda. The distribution of theta, let's call this lambda. Okay, let's call this p theta for simplicity here. This is the prior. Okay, the prior and theta, that gives me a bit. So if you calculate this expectation, that's really the weighting of the risk. That's what we do. And this turns out to be just the expectation of this. And this is more interesting in a sense, because this is saying I take the loss of theta and delta x and take the expectation over the joint randomness of theta and x. Okay, so this is the Bayes risk. So this is averaged over all the randomness in the model. So you have loss, you have your parameter, you have your estimator, both are random. So this loss is going to be random, doubly random. And I take the expectation, averaging it out over everything, over the randomness of x and theta jointly. This turns out to be equal by the smoothing property to this. Averaging out of the frequentist risk. It's the same thing, and the same thing is called the Bayes risk. And I'm calling it really here. I'm referring to the prior distribution here as lambda. This is just a notation. It's like mu, or like Hiss's distribution. So this is going to be really a function of the distribution, the prior, and delta. We're sort of out of time. But next time we're going to come back and see that posterior gives you a way. So now I can minimize this. I can ask which decision rule minimizes it. If I fix my prior, what is the decision rule that minimizes this? And there's going to be like a good answer to this, because it's just a number for each estimator. I fix my prior, so I can compare them. That will be for the next time, and hopefully we'll see more of the Bayesian analysis. Thank you, guys. See you next time.